The wind that howls across the frozen surface of the Amur River carries a bite that settles deep in the bones, a chill so profound that it seems to freeze time itself here in the Russian Far East. We are standing on the edge of the world, over 6,000 kilometers from the political centers of Moscow, in a city carved out of the taiga by the desperate hands of forced laborers and the fervent idealism of young Soviet pioneers in the 1930s. This is Komsomolsk-on-Amur, a forbidding industrial fortress where the temperature frequently drops to 40 degrees below 0 degrees Celsius, a cold so intense that exposed skin freezes in minutes and steel becomes brittle enough to shatter like glass under impact. Yet, in this desolate landscape, hidden behind miles of perimeter fencing and guarded by layers of security that recall the height of the Cold War, lies the beating heart of Russian aerospace power. This is the Komsomolsk-on-Amur aircraft plant, known by its heavy industrial designation as Knyaz. It is here, in the shadow of Sopka Hills and amidst the relentless snow, that Russia forges its deadliest predatory birds, the Sukhoi Su-35 and the fifth-generation stealth fighter, the Su-57. To understand these machines, you cannot simply look at a spec sheet. You must understand the brutal, unforgiving crucible in which they are born. The scale of the Knyaz facility is difficult to comprehend without walking its floor, as the plant operates not merely as a factory, but as a self-contained industrial city-state that covers territory the size of a small European municipality. Imagine a space so vast that workers commute between assembly halls on buses that never leave the factory gates, navigating a labyrinth of concrete and steel that has been expanding and mutating since 1934. The facility is a living timeline of aviation history where crumbling brick workshops from the Stalinist era stand shoulder to shoulder with gleaming, hermetically sealed clean rooms designed for the 21st century. It is a place of profound contradictions where gray-haired master craftsmen use hand files to perfect parts with a touch as delicate as a watchmaker, while just meters away, massive robotic arms dance with programmed precision. This juxtaposition of the archaic and the futuristic is not an accident, but a necessity of Russian engineering philosophy, which values rugged survivability as much as high-tech performance. If detailed technical breakdowns of heavy industrial engineering and extreme manufacturing interest you, subscribe. I have got more of these coming. The story of Knyaz is the story of metal, fire, and the stubborn refusal of human engineering to bow to the laws of nature. Stepping inside the primary fabrication hall, the first thing that assaults your senses is not the sight of aircraft, but the overwhelming metallic taste of the air. It smells of ozone, hot oil, and the dust of a million grindstones, a sensory cocktail that signals the violent transformation of raw matter. Here, the journey begins with the foundational elements of modern aerial warfare, titanium and aircraft-grade aluminum alloys. These materials arrive in massive, dull ingots, appearing more like debris from a quarry than the skin of a supersonic fighter. Titanium, in particular, is a notoriously difficult metal to tame. It is light, incredibly strong, and heat-resistant, but it fights back against every attempt to shape it. To work with titanium is to engage in a metallurgical wrestling match where the material itself seems to have a will of its own. Processing this metal requires hydraulic presses of staggering power, machines that loom over the shop floor like iron giants from a bygone age. When the operator engages the main press, the ground beneath your feet trembles with a low-frequency shudder that travels up through your boots and rattles your teeth. This press exerts tens of thousands of tons of force, a pressure equivalent to balancing the entire weight of the Eiffel Tower on a typical dining room table. Under this unimaginable stress, the stubborn titanium ingot surrenders, flowing like stiff clay into the die to form the structural bulkheads that will eventually hold the aircraft together under 9 times the force of gravity. The sound is not a crash but a deep resonant groan, the scream of metal being forced against its molecular lattice. There is a distinct atmosphere in these heavy press shops, a feeling of ancient, heavy quiet that exists between the thunderous cycles of the machinery. The air is thick and still, lit by the yellowish glow of high-pressure sodium lamps that hang from the rafters far above, obscured by a permanent haze of industrial particulate. Workers here move with a slow, deliberate cadence, their movements economical and practiced. There is no running, no shouting, only the silent language of hand signals and the watchful eyes of men and women who know that a mistake with a 50,000-ton press does not result in injury, but in erasure. It is a cathedral of brute force, where the sheer mass of the machinery commands a reverent respect from everyone who walks the concrete floor. Once the rough shapes are forged, the process transitions from the violence of the press to the surgical precision of the milling centers. This is where the Knaus facility reveals its modernization, moving from the soot-stained heavy industry of the 20th century into the digital reality of the 21st. The structural components, now roughly shaped but still raw, are loaded into massive 5-axis CNC milling machines. These machines are the sculptors of the modern age, capable of attacking the metal from virtually any angle. The milling head spins at speeds exceeding 20,000 revolutions per minute, a speed so fast that the cutting tool becomes a blur, singing a high-pitched, dentist drill whine that cuts through the lower rumble of the factory. As the cutter engages the metal, it shaves off ribbons of shimmering aluminum and titanium, creating a shower of sparks and metallic confetti that is constantly washed away by flood currents of milky white coolant fluid. This coolant is vital, for the friction generated at the cutting point creates temperatures hot enough to warp the metal or even weld the tool to the workpiece instantly. The tolerances here are measured in microns. A micron is 1,000th of a millimeter, or roughly 1/50th, the thickness of a human hair. If a critical bulkhead is off by more than a handful of microns, it is scrap metal. The entire component, representing hundreds of hours of labor and thousands of dollars in material, becomes a useless paperweight. There is a hypnotic quality to watching these machines work, a relentless rhythm of creation that continues 24 hours a day, 7 days a week. The operator stands behind thick safety glass, watching monitors that display the tool path in a cascade of green coordinates. Inside the machine enclosure, a mist of vaporized coolant hangs in the air, creating a ghostly atmosphere where the violent removal of metal happens in a sealed, wet world. When the cycle finishes and the doors slide open, the rush of warm, humid air that escapes carries the smell of wet metal and chemical lubricants, a scent that clings to the clothes and hair of every machinist who works the line. It is a moment of calm before the next billet is loaded, and the screaming song of the spindle begins again. From the machining centers, the thousands of individual parts migrate toward the assembly halls, vast caverns of light and space where the aircraft finally begins to take a recognizable form. This is the domain of the jig, the massive steel scaffolding that cradles the aircraft's skeleton as it is built. These jigs are engineering marvels in their own right, massive yellow and blue steel cages that are permanently bolted to the seismic reinforced floor. They must be incredibly rigid, for they serve as the absolute reference point for the entire aircraft. If the jig shifts by a fraction of a millimeter due to thermal expansion or ground settling, the aircraft built inside it will fly crooked, or worse, tear itself apart at supersonic speeds. The assembly process of a Sukhoi fighter is a hybrid of automated positioning and manual labor that has remained largely unchanged for decades. While laser trackers verify the alignment of the fuselage sections, teams of riveters swarm over the structure like diligent insects. An aircraft like the Su-57 contains hundreds of thousands of rivets, each one a potential point of failure if not installed correctly. The process is deafening and physically exhausting. One worker, the bucker, holds a heavy steel block against the back of the rivet, while on the other side of the aluminum skin, the gunner drives the rivet home with a pneumatic hammer. It is a violent percussive dance that repeats endlessly, a machine gun staccato that fills the hall with a wall of noise so dense you can feel it vibrating in your chest cavity. Imagine trying to thread a needle while riding a jackhammer. That is the level of concentration required to set a rivet perfectly flush while your arms are vibrating violently. A rivet that sits too high disrupts the airflow. A rivet that sits too deep weakens the skin. The workers develop a rhythm, a tacit communication where the change in the pitch of the rivet gun tells the partner on the other side exactly when the rivet is set. Between these bursts of noise, there are long pauses of silence as they reposition, wiping sweat from their brows despite the cavernous size of the hall. The floors here are polished concrete, kept meticulously clean to prevent foreign object debris, or FOD, which is the mortal enemy of aviation. A single lost washer or stray wire clipping left inside a wing tank could cause a catastrophic failure mid-flight. As the airframe comes together, the complexity of the internal plumbing becomes apparent. Before the skin is fully closed, kilometers of hydraulic lines, fuel pipes, and electrical wiring must be woven through the ribs and bulkheads of the fuselage. This is the nervous system and the circulatory system of the beast. The hydraulic lines, made of stainless steel, are bent to precise geometries to snake around structural members. These lines carry fluid at pressures exceeding 3,000 pounds per square inch. To visualize this pressure, imagine the force of a great white shark's bite concentrated into a stream of fluid no wider than a pencil. A pinhole leak at this pressure acts like a water jet cutter. It can slice through bone and tissue instantly, making the inspection of these lines a matter of life and death for the maintenance crews who will service the plane later. The installation of these systems happens in the cramped, claustrophobic crawl spaces inside the fuselage. Technicians, often selected for their slight build and dexterity, must contort their bodies into impossible shapes to tighten connections deep within the wing roots. It is dark inside the unfinished aircraft, lit only by the harsh glare of portable work lights that cast long, dancing shadows against the green zinc chromate primer that coats the interior metal. The air inside these confined spaces quickly becomes stale and hot, smelling of sealant and rubber. It is a silent, suffocating struggle against geometry, where patience is the only tool that matters. One crossed wire, one loose B-nut on a hydraulic line, and the aircraft is a ticking time bomb. Once the skeletal frame is rigid and the skin is flush, the hollow beast requires a heart capable of breathing fire into the freezing Siberian air. For the Su-35 and the early production Su-57, this heart is the Saturn AL-41F1S engine. These engines are behemoths of titanium and nickel superalloys, capable of generating over 14.5 tons of thrust each in afterburner. But raw power is not their only trick. These engines are equipped with three-dimensional thrust vectoring nozzles. Unlike a standard jet engine that pushes only backward, these nozzles can articulate, pointing the exhaust stream up, down, or to the sides. This allows the 30-ton aircraft to dance in the sky, performing maneuvers that defy aerodynamic logic, such as the Pugachev's Cobra, where the plane rears up like a striking snake, hanging suspended in the air on a column of raw thrust. Installing these engines is a delicate operation that feels incongruous with their immense power. The engines are moved on specialized dollies that glide on air cushions, hovering millimeters above the floor to ensure absolutely zero vibration during transport. The clearance between the engine and the airframe is measured in millimeters. The technicians guide the multi-ton turbine into the fuselage bay with gentle touches, watching the gaps like hawk-eyed sentinels. It is like sliding a grand piano into a glove compartment. When the engine finally seats into its mounting points with a heavy metallic clunk, A collective sigh of relief ripples through the team. After the intense focus of engine installation, the factory floor offers a moment of visual respite, though the work never truly stops. The vastness of the final assembly hall is humbling. You can look up and see the complex truss work of the ceiling obscured by a blue haze of distance. In the winter, despite the heating systems, the outer walls of the hall radiate a chill that reminds everyone of the frozen world outside. It is a quiet reminder that this high-tech marvel is being built in a place that is fundamentally hostile to human life. Workers warm their hands on cups of tea during breaks, their breath sometimes visible in the colder corners of the shop, discussing production quotas and the bitter wind waiting for them at the end of the shift. For the fifth-generation Su-57, the process now takes a detour into the highly classified world of stealth coating. The aircraft is moved into a restricted access paint facility, a sealed environment where the air is filtered to a level of purity that rivals an operating room. Here, the plane is coated in radar-absorbent material, or RAM. This is not paint in the traditional sense. It is a complex chemical matrix designed to trap and dissipate electromagnetic waves, turning the aircraft into a black hole on radar screens. The application of RAM is closer to laboratory chemistry than industrial painting. The thickness of the coating must be perfectly uniform across complex curves. A variation of a fraction of a millimeter can create a hotspot that reflects radar energy, rendering the stealth characteristics useless. The spray robots that apply this coating move with a spooky, silent grace, their arms articulating with fluid motions as they lay down the toxic gray matte finish. Humans in the room wear full-body protective suits with independent air supplies, looking like astronauts exploring an alien derelict. The solvents used in these stealth coatings are incredibly harsh, and the fumes are strictly contained. The atmosphere in the paint shop is sterile, clinical, and tense. There is no noise of rivet guns here, only the soft hiss of the atomizers and the hum of the massive ventilation fans that cycle the air completely every few minutes. Applying this coating is like trying to wrap a complex geometric shape in a layer of liquid velvet that dries instantly and must be perfectly smooth. Knowing what you now know about its real-world production bottlenecks and extreme hazards, do you think the massive capital investment in this facility was worth it? Share your thoughts below. The stark contrast between the sterile, toxic silence of the stealth coating chamber and the rugged exterior of the plant is jarring. Outside, the snow piles up against the corrugated metal walls, and the logistics of keeping this factory running become a battle against geography itself. Every component that isn't made on site must travel thousands of kilometers. The supply chain for Kaneaz stretches across the entire Eurasian landmass. Train cars loaded with sub-assemblies rumble slowly across the Trans-Siberian Railway, battling blizzards and delays, taking weeks to arrive from suppliers in European Russia. This logistical fragility is the hidden vulnerability of the plant, a high-tech island in a sea of frozen wilderness, dependent on a steel umbilical cord of rail lines to survive. Once the aircraft is fully assembled and coated, it must undergo the most critical phase of its birth, the systems check. This is where the aircraft wakes up for the first time. Mobile power units, loud diesel generators, are hooked up to the plane, pumping electrical power and hydraulic pressure into its veins. The cockpit lights up, a Christmas tree of multifunction displays and warning lights. Test pilots and senior engineers sit in the cockpit, running through thousands of lines of code and checklists. They cycle the flight control surfaces, the ailerons, elevators, and rudders, watching them twitch and flutter like the feathers of a waking bird. They test the radar, the electronic warfare suites, and the targeting systems, ensuring that the millions of lines of code interact seamlessly with the hardware. But the true test of a NAS bird is not in the warm hangar, but out on the flight line. This is where the climatic chamber testing meets reality. The aircraft is towed out of the massive hangar doors into the biting cold of the airfield. The temperature might be minus 35 degrees Celsius. The aircraft is left to cold soak, sitting on the tarmac until its entire structure, every drop of oil, and every microchip is chilled to the ambient temperature of the Siberian winter. This is a brutal test that Western aircraft rarely face to this degree. The engineers want to know if the hydraulic seals will crack, if the liquid crystal displays will freeze and shatter, if the engine lubricants will turn into glue. Standing on the tarmac during a cold soak test is an exercise in endurance. The wind cuts through the thickest parkas, and the cold radiates up through the soles of boots. The aircraft sits silent, a dark silhouette against the gray snow and the pale, watery sun. It looks dormant, almost dead, a metal sculpture abandoned in the ice. But this is the moment of truth. If the aircraft cannot start here, in the heart of the motherland's winter, it is useless to the Russian Air Force. The ability to operate from frozen, austere airfields is a core requirement of Russian doctrine, a legacy of a military strategy that assumes the comfortable air bases will be the first to be destroyed in a major war. When the order is given to start, the Auxiliary Power Unit, or APU, winds to life, a high-pitched scream that pierces the frozen air. Heat haze begins to shimmer from the exhaust port, blurring the snowy horizon. Then the main engines are engaged. The low rumble builds to a roar as the turbines spin up, compressing the freezing air and mixing it with fuel. Ignition. A blast of blue-orange flame erupts from the rear, stabilizing into a steady torrent of heat. The snow behind the aircraft instantly melts and vaporizes, creating a massive cloud of steam that envelops the tail. The sheer thermal shock of 0 to hundreds of degrees in seconds is a torture test for the materials, expanding the metal rapidly while the rest of the airframe remains frozen. The test pilot, bundled in flight gear that looks bulky and cumbersome, taxis the aircraft to the runway. The tires crunch over packed snow and ice. The Kanaz airfield is not a pristine, heated runway. It is a slice of the real world. As the pilot pushes the throttles forward for the takeoff run, the afterburners kick in. The noise is cataclysmic, a physical blow that shakes the snow off the nearby pine trees. 2 pillars of fire propel the 30-ton machine down the runway. It accelerates with terrifying speed, kicking up a rooster tail of snow and ice crystals that sparkle like diamonds in the exhaust wake. Then, with a subtle pull on the stick, the nose rises, and the Su-57 leaps into the gray sky, defying the gravity that tries to hold it to the frozen earth. Seeing a fighter jet take off in these conditions is a visceral reminder of the raw power involved. It is not just physics, it is a violent assertion of will. The ground crew watches, hands over ears, feeling the reverberations in their chests long after the plane has disappeared into the cloud layer. The smell of burnt jet fuel hangs heavy in the cold air, a pungent perfume of industrial success. They know that up there, at 10,000 meters, the pilot is putting the machine through high G turns and supersonic sprints, testing the limits of the rivets they drove and the welds they inspected. It is a moment of shared pride, a silent acknowledgement that their labor has produced a creature capable of mastering the sky. Yet the story of Kanaz is not just about the machines, it is about the people who build them. Many of the workers here are second or even third-generation factory employees. Entire dynasties of families have worked at the plant since the Great Patriotic War. They speak of the factory not as an employer, but as the lifeblood of the city. Without Kanaz, Komsomolsk-on-Amur would likely wither and die, reclaimed by the taiga. This deep generational connection creates a unique culture on the factory floor. There is a sense of ownership, a grit that comes from surviving both the harsh climate and the economic turbulence of the post-Soviet years. They have seen the factory go from churning out thousands of simple aircraft to handcrafting small numbers of incredibly complex ones. However, this legacy is under threat. The plant faces a demographic crisis as the older generation of master craftsmen retires. Replacing a worker who has 30 years of experience with titanium welding is not a matter of simply hiring a trade school graduate. The tribal knowledge, the unwritten tricks and instincts developed over decades, is being lost. The plant is trying to bridge this gap with automation and digital training, but a robot cannot replicate the intuition of a master mechanic who can tell if a bearing is bad just by listening to the pitch of its vibration. This human element is the ghost in the machine, the variable that determines whether a factory remains a center of excellence or becomes a hollow shell of its former glory. The sanctions imposed on the Russian aerospace industry have added another layer of complexity to the struggle at Kainaz. While the airframes are pure Russian metallurgy, the modern avionics, the brains of the aircraft, historically relied on global supply chains for microchips and high-tech components. The plant has had to pivot painfully toward domestic substitution and alternative suppliers. This silent war is fought not on the battlefield, but in the procurement offices and engineering labs. Engineers are forced to redesign circuit boards to accept slightly larger, less efficient domestic chips, or to find creative workarounds for missing technologies. It is a game of engineering improvisation, forcing the integration of new tech into old designs, like trying to install a modern smartphone processor into a 1990s desktop computer. The result of this struggle is an aircraft that is a paradox, physically imposing, aerodynamically superior, but internally a patchwork of brilliant adaptation and forced compromise. The Su-57, for example, has seen a slow and difficult gestation period, with production rates lagging behind initial promises. Each aircraft that rolls out of the heavy doors at KNAAZ represents a triumph over immense headwinds, political, economic, and logistical. It is a testament to the stubborn resourcefulness of the engineers who refuse to let the factory stop, regardless of the obstacles placed in their path. As the sun sets over the Amur River, casting long purple shadows across the snow-covered runway, the factory lights hum to life, illuminating the steam rising from the vents. The night shift is beginning. Inside the warm halls, the rhythm continues, the pounding of rivet guns, the whine of milling machines, the hiss of welding torches. The work at Nez never truly sleeps. It is a relentless cycle of creation in the face of entropy. The aircraft built here are destined for the front lines, for the geopolitical chessboards of the Middle East, Europe, and Asia. They are instruments of state power, forged in the coldest corner of the empire, designed to project heat and violence thousands of miles away. There is a strange, melancholy beauty to the scene outside the gates. The city of Komsomolsk-on-Amur is quiet, the streets empty in the deep freeze of the evening. The smoke from the factory's power plant rises straight up into the still air, a white column connecting the earth to the stars. It is a reminder of the isolation of this place, a city built on the edge of nowhere to build the machines that rule the skies. The people here live and die by the fortunes of the plant. Their history is written in aluminum and titanium, in the roar of afterburners and the silence of the snow. Ultimately, the Komsomolsk-on-Amur aircraft plant is more than just a manufacturing facility. It is a monument to a specific kind of industrial heroism. It represents a worldview that values scale, durability, and the ability to operate in the worst conditions imaginable. It is a place where the finesse of high technology meets the brute force of heavy industry, a collision that produces some of the most capable and feared aircraft in the world. Whether these machines are seen as marvels of engineering or instruments of war, the sheer feat of their creation in such a hostile environment commands a certain awe. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching. The lights of the factory burn on through the Arctic night, a beacon of fire and ice, forging the wings of a superpower one rivet at a time.